So if you go to the notebooks page, you will see one demonstration notebook about programming assignment 1. This gives some basic commands that you need to start playing with the data, right? So the data for this programming assignment, I'm assuming you have gone through the assignment description. It is a very long description, but the amount of work that is needed is not that much. So don't get intimidated by the 7 pages. Because the reason it is big is because we have also provided the derivations for you. You don't have to calculate the gradient and everything. So that's why there's a lot of discussion. And this week we'll primarily be looking at those derivations in the class as well. So please pay extra attention. All right. So I'll just take 2 minutes to go through this workbook. The data that you will be analyzing is a set of handwritten digits. All right. It is in this file, and this is a MATLAB file, but you can load it in Python as well if you use the load mat routine in the SciPy library. All right. The data that is arranged in a strange way. All right. So so when you look at it, you'll see that it's basically a collection of data sets inside, right? So they have names. So there's test 1, test 2, test 3, all the way to test 9, and train 0 through train 9. Sorry. All right. So what this means is that each of these data structures contain the data for one type of digit. Okay. So each data object in this case is a digit. All right. A digit as an image. Right. So there are 10 digits. So each one of them is for one digit. So test 0 means it has lot of examples of written zeros. So somebody wrote 0 in many ways, right? So they collected all of that. Same way for all of these, right? The reason they are test and train is that your training data is from here, and then you will develop your neural network, and then you will test it on the data over here, right? So for example, I have shown here that this is how you get all the data for training examples for digit number 9. All right. So you can go through this later, but essentially if you look at this matrix of train 9, this is a 5949, 784. It's a matrix, these many rows and these many columns. Each row is a digit. Okay, so each row corresponds to an object of a digit, right? So there are 5,949 images of zeros in this data set for the training data, all right, for digit 9. And same way you can look at train 0 through train 9. Each row has 784 columns, which means that the number of attributes that you have are 784. All right. Now, if you want to visualize them, so the way this data is created is that you have an image. Okay, so the image is actually so what they did was they made somebody write a 0, right? And they took an image of that. This image is 28 by 28 pixels. So there are 28 cross 28 pixels in this image, right? Some of them will have higher intensity wherever it is 0, and others will be low intensity. What we do is we sort of flatten this matrix. Okay, so flatten means that you take first column, you make it the first, so you keep putting them like this. So each column you keep appending to a long vector. All right. So this process is called flattening. So since there are 28 cross 28 entries in this matrix, this will be 28 cross 28 length vector, which is 784. All right. So that's the data you will be dealing with. Right. So don't worry if you don't see the digit when you look at the data. The way to look at the digit is that you take any. So what you do is you take any digit, any row of this matrix, and then you reshape it. Now in MATLAB, and so that's the opposite process of flattening. In flattening, we just take the matrix and you put it into one long vector. If you put all the, these components back into a matrix, that's called reshaping. So if you reshape it, this is how it looks like. Okay, so I have plotted like 100 of those 5949 digits here. So each one of them is your data object. Okay. So this is 9. Then you can also look at other images as well. So your task is to build a neural network or a classifier which will learn from this training data, and then when I give it a new image, it needs to tell me if which digit this is, right? So that's the handwritten digit recognition problem. This has a special place in Buffalo because UB Computer Science Department is one of the pioneers of handwritten digit recognition and handwriting recognition. So a lot of the work that went around here in the Cedar Center way 20 years back and after that has been used in USPS and many other postal services around the world to do automatic address reading, right? So one part of that was this digit recognition. So that's why sort of we feel especially proud to sort of look at this problem. But anyway, for your training, for your assignment, this is the data you have to work with, and then there are some other basic routines that you can use to manipulate this data. Okay, any questions so far? All right, so I'll suggest that you start sort of playing around with this data set. I'm hoping you already have created your groups and everything. But start playing with this data and start working on it early on. This is big data also because there are around 60,000 images that we have. So when you run this training and testing, it takes time. So please give enough time. Don't start on the last day because you won't have enough time to actually run the whole thing. All right, so let's go back to our discussion from last week. All right, so let me set the stage for this. Well, let me leave it here. So what we are looking at right now is how to train a perceptron. How to train a perceptron in the setting where the data is not really separable by a line, right? So then we said that the best answer that we can get is the one that makes minimum error on your training data. Okay, so we defined the error function here, which is a function of your weights, because the weights is what you want to learn. This W vector is the equation of the line that you want to learn, and you want to learn the one that gives you the minimum error. Right? So we defined the error. A little bit of notational change that we made was that we are now going to assume that each training example is represented as a bold X of I. This is the ith training example, and this is the label associated with bold with this example. All right. We also assume that this label is no longer binary. It could be anything. It could be binary, but it could be any value. All right. And then we define this. This is essentially, if W is your weight, then this is what your prediction will be on a new example, right? So this will be your error, how far you are from your true value. And then when you take a square, you're taking a square because you want to deal with the magnitudes. And then we put a half here, and then this is the total error for this training data. Now you can define the error in many other ways as well. For example, you could also put an absolute sign here. That okay, I'm also only going to look at absolute signs. You can put any scalar here. You can put half, 3, 4, anything. It doesn't matter. Whatever weight that you will get will be the same because the weight doesn't really depend on those constant values. All right. Okay. So now our task is how do we optimize for this, right? So the one thing that we have seen in mathematics is that if you want to optimize over a function, you can take the derivative, right? And then when you take the derivative and set it to 0, the value that you get would be the answer at which the function is minimum or maximum. And then later you can check for the second derivative to see if it's maxima or minima, right? That's a standard way. However, when you are dealing with complex functions, setting the derivative to 0 is not very easy, right? So the reason being, so this is minimizing or maximizing a function, right? Sometimes together we call them optimizing for a function. So let's say you have some function e of w, and you want to find the w at which this value is minimum, e of w is minimum. So one way I said was, you can say d of d, and we set it to 0, right? So for example, let's say we assume that our w is just 1 element. It's not a vector, it's a scalar, right? So let us say that W is just assume W is a scalar, right? And assume that E of W is 2W square minus 4W plus 2, right? So the easy way to do that is you set this to the derivative of this to 0, which will be 4W minus 4 equal to 0, implies that W equal to 4, right? So at this value, you'll get the optimal value. That's basic math, right? However, what happens is that sometimes it might not be easy to set this to 0, right? So for example, another example. W is 1, right? Yeah, that's true. Thank you. I was just testing you guys. Another example is E of W is equal to something else. Let's say log of W plus e to the power minus 4W plus 6W square plus 9, right? Something. So what happens is that you can still perform the same procedure, but it might not be easy to get. When you set E prime W equal to 0, it might not be easy to set to get the W for which this is 0, right? It is only easy to do when this is a linear system of equations. So sorry, when the derivative is a linear system of equation, you can solve it, right? So for example, here we could solve it because this system of equation was linear in W, right? But if it is not, then it becomes challenging, all right? Same thing happens if W is a vector, right? So let's say W is a vector which has two elements, W1 and W2, right? So in this case, let's say E of W is 4W1 square plus 6W2 square minus 4W1 minus 6W2 or let's say 12W2 plus 8, right? So this is the error function. You can set the derivative of this to 0, and what you will see is that this will give you an answer, right? I think W1 will come to 0, to 1, and W2 will come to 2, right? Why? Because the derivative is a linear system of equation, right? But again, this could be more complex than that, right? For example, if E of W is something else. Let's say it is 4W1 square plus 6W2 square plus 2W1 times W2 minus 4W1 plus something 8, right? Then it becomes harder to sort of set it, right? So which means that straight setting derivative to 0 might not work in all cases, right? So now how do you optimize for those kind of functions? So there are many routines available, especially if the function is convex, and one of them that we talked about last time was gradient descent, in which what you do is you, instead of directly minimizing it, you perform an iterative procedure where you assume that your W is something, and then you move along the gradient of the function, and if the function is convex, then you're guaranteed to reach the optima. And so that's gradient descent. All right. Any questions so far? All right. So let's see. Okay. So the gradient descent algorithm is a general algorithm which is fairly straightforward. It looks like this. Right. So it looks like this. What you do is you start with some value of W, start from any point in your variable space, right? And then you move along the direction of the steepest descent, all right? And that way, and this is if you are trying to reach the minima. If you're trying to reach the maxima, then you move along the steepest ascent, right? So the next question becomes, how much do you move by? And that is given by some learning rate. And then the next is, what is the direction of that steepest ascent or descent, and we have seen this is also from math that is given by the gradient of the function at that point. So the gradient of a function essentially points in the direction, like a tangent of the curve, right? It points in the direction where you would, if you move in that direction, that is the maximum direction you'll move in, right? That is I won't go into that, but if you want to look at it, if you look at the class notes for these slides, I have a little section about how that comes about using sort of the Taylor series expansion of a function around a point, right? I'm assuming you know that part. But anyway, so for now, let's just take it from me that the direction of the gradient gives you the direction of the steepest ascent. So then your gradient descent algorithm becomes very easy. At every step, you compute the gradient and then you move in the opposite direction. That's why there's a minus here. And by how much? By some quantity here, eta, right? So eta, we set it to something. It basically tells you how much you want to move by, right? Now the reason, so far I was talking about derivatives and suddenly here I have a gradient. The reason for that is because if your function is a function of a vector, right, instead of just a w1 scalar, then the derivative is also known as the gradient, right? Because the way you compute that is by taking the derivative of that function with respect to every entry in this, right? So it's basically a partial derivative of e with respect to each of these scalars, and you stack them up into a vector. So the gradient of a function will also be a vector, right? Even though the function value is scalar, right? The function value that you have here is a number, right? It's a scalar value, but the gradient of that with respect to a vector will also be a vector, right? So the idea is very simple. You start somewhere on this. So this is the function. You start somewhere, and then at every step, you move along the direction of the steepest descent, and finally you'll reach the answer, right? So now if you want to use it for perceptron learning, the only thing you want to do is to compute this gradient, right? If you can compute the gradient, then you have a training algorithm, right? This is the training algorithm, just a for loop, keep going. And then there's also a notion of convergence, which I'll talk about quickly. All right. And one way you can sort of simplify it is that, look, this is a vector, right? So you can also compute the update for each element of this vector, right? And then you just stack it into that vector. So the wj, the new wj will be your old wj minus eta times the derivative of e with respect to wj. Okay, here the gradient is replaced by derivative because you're taking the derivative with respect to a scalar, right? So is this clear? This is, yes, go ahead. Oh, the reason we are moving in the opposite direction, which means the reason there is a negative sign here, is because we want to find the minima. All right, the gradient points along the steepest ascent. So if you move along the gradient, you're moving in the direction where the maxima will be. If you want to reach the minima, you will go in the opposite direction. The reason we want the minima is because we are trying to minimize the error function, right? Because we want the lowest error. That's why. Any other questions? Yes. Uh-huh. Right. Okay, so that's another good point, and I actually omitted that, but thank you. So the question is that for the perceptron, you might be able to, write it in this form. You might be able to write it in a linear form and set it to 0, right? It might work, but even there, the reason we don't prefer to do that is that, see, what does this mean, right? When you compute the gradient here, and then when you set it to 0, you're trying to solve a system of equations, right? Because you're trying to find the solution in which you're trying to find W1, W2 up to WD, which agrees with this, right? So you're trying to solve a system of equations. Now, if your D is very large, which means that you have a lot of variables, then solving that system of equations becomes very complex. In the sense, it's typically order D to the power 3, right? If you if you remember your linear algebra, if you are trying to solve a system of equations like this, ax equal to b, right, where your a is some d cross d matrix, and x of course is a d cross 1 vector, and this is a d cross 1 vector, right? If you're trying to solve an equation like this, one way to do that is you can say x equal to a inverse of b, right? But computing an inverse of a d cross d matrix is order d cube, right? So it becomes computationally challenging. The other problem is that many times this might not be well, it might not be a well conditioned matrix, which means that computing the inverse might not be numerically possible, right? Because there might be singularities in this matrix and all those issues. So computing a direct inverse often becomes tricky. So it's computationally challenging, and second is that if the matrix is not very well conditioned, then finding this also is a challenge. So to avoid this, right, we use gradient descent, right? Okay, so now the next thing we are going to do is we are going to derive the gradient for perceptron. All right, because gradient descent is a general algorithm. It has nothing to do with machine learning. We are just using it for perceptron, right? So the thing we are going to discuss now is how to use, I'm going to just write GD, gradient descent, for perceptron learning. All right, so the basic algorithm will stay. The only thing that we need is compute the gradient of your E of W. Right, this is what we need, where E of W is equal to 1 by 2 summation I equal to 1 through n, or n, what do I use? N is the number of data points we have, right? Let's assume there are n data points. Yi minus W transpose Xi square. All right, so now let's try to do that. Okay, now I mentioned earlier that gradient can also be written as, basically you can take the partial derivative with respect to each entry and so on, and then and just put it in a vector, right? So now we'll see, okay, how to compute the derivative with respect to any jth entry of this vector. Okay, so W is a vector. We are going to compute the derivative of jth entry, and then that way we can create the gradient, right? So let's do that. So this will be equal to d by d of Wj half summation I equal to 1 through n yi minus W transpose Xi, right? So the Wj is hidden in this W. This is a vector, right? So I'm going to just open it, half I equal to 1 through n yi, right? And this is the inner product, right? So you can also write it like this. This is W1 xi1 plus W2 xi2 plus somewhere there will be Wj xij plus Wd xid square. Any questions about this? I'm just opening that inner product. The reason I'm doing that is that way you can see that you just need to, you see where the Wj is, right? So now if you try to compute this, right, this will become d by d Wj half, right? Sorry, we can put the derivative inside the summation, right? It's just a summation, and then the derivative of this with respect to Wj will be, first you take the derivative of this with respect to this, so that will give me 2 times yi minus W1 xi1 Wd xid times derivative of this inner part with respect to Wj. Now see, this is not dependent on Wj, so this goes away. All of these entries are not dependent on Wj except for this one, so this will be just minus xij. All right, any questions so far? Okay, so this is fairly straightforward, and this 2 cancels with 2. That's why we had that 2 earlier, just to make that easy, but that's not very important. All right, I'm going to write it again as this. So it will be summation I equal to 1 through n yi minus W transpose X I times Xij minus. Alright, so this is the derivative of this error function with respect to the jth entry of this vector. Alright, so now we can put them all in a vector and create the gradient, even though we don't really need the gradient. So the gradient delta of E of W will be minus I equal to 1 through n yi minus W transpose xi times xi1 and so on, right? So every time this is replaced by the index of the row xi xid. All right, any questions so far? Perfect. So this is the gradient, right? So now we can easily do our updates. So what we will do is, so our GD perceptron learning will go like this. Step number 1, we initialize W is our vector, right? To something, right? Let's say we initialize it to all zeros, 0, 0, right? And this, I'll come to this, that this is important. The second thing is, while not converged, and I'll come to this later, but let's say there is some way we can say that, okay, have we reached the solution? While not converged, what we will do is we will say W of J is equal to the old Wj. So Wj is essentially the jth entry from W, this weight vector, is this minus eta times d of dwj of E of W, or I should just write it like this, or Wj is minus eta, because I derived this, right? So this is going to be okay. So this is our update rule for every entry of this vector. So you do it for all j, 1 to d, right, or 0 to d, however you are doing your indexing. But and then you keep going back, right? So this is the basic algorithm. You can also implement it very easily. The next question becomes that how do we initialize, how do we set the convergence, assess the convergence, and what is eta? All right, there are three things. What is the importance of eta? So I'm going to go through them one by one. So the convergence is easy. You can check for convergence by saying, okay, did the entries of Wj change at all, right? So if you think about that graph again, right? So let's say you're trying to find the minima. Once you reach the bottom, you will see that the gradient will be 0 at the bottom, right? Which means that your weight will no longer change, right? So once you reach the minima, because of the definition of the minima, the gradient will be 0, right? Which means all these entries will be 0, which means that you would not be updating anymore. Right. So in your program to check for convergence, all you see is you just check if, so convergence will be check if all Wj's do not change. So if they are not changing, that means you have reached the bottom. All right. And typically, so this is a very ideal situation. And then eta basically tells you how much you jump by. Right? So if your function is perfectly convex, right, like the function that I showed you in the slide, then it doesn't matter where you start from. It doesn't matter what you will reach the minima, right? But this eta is important. What eta tells you is how much you jump by. So I was giving you an analogy of actually going down a hill, right? If you take very small steps, your eta is very small, that means you will take a long time to reach the bottom, right? You will reach the bottom, but you might take very long time. So you do not want a very small eta. right? But if you take a very large eta, what will happen is that your steps are very large. So it's possible that you might overshoot the minima, right? You might just jump over it, and so you don't want the eta to be too large either. But setting etas, there is no principled way to do it. You kind of sort of do it, by trial and error. All right. However, all these things become even more important when your data is not really convex. So let's say your data has some local minima, right? So what will happen in the real setting? So ideal function should look like this. Even in one dimension, it should look like this, right? Then you can reach here wherever you start from. But real functions will actually look like this. Right? So this is where you want to reach, but there are these things where the gradient is 0. But the gradient is 0 because of, even though they are not minima, they are local minima, right? You do not want to get stuck in the local minima, right? But the problem is that this perceptron learning, the problem with perceptron learning is that depending on where you start from, there is a chance that you can get stuck in local minima, okay? So to avoid that, what typically people do is that they run this algorithm many times, every time starting from a different initial value. All right, so they start from here, maybe they get stuck here, sometimes they start here, stuck here, sometimes they'll come here and they will reach the minima. And every time you see what is the value that you got, and then you take the minimum of that. So that's one way to overcome that issue. But the point that I'm trying to make is that the initialization is important. It is important where you start from. Even in this setting, right, you're trying to reach here. If you start from here, you will take longer to reach here. If you start here, you will take shorter. Though you do not know where to start from, right? But what you initialize it with will influence how fast you reach your convergence, all right? So initialization is important. The length of eta is important. And there's one more thing. Those two things are important, right? So that is the gradient descent algorithm for perceptrons. Any questions so far? What's that? Eta. Oh, right. So eta is a number, right? So eta you can, so what we've discussed is that you do not want eta to be too large or too small, but there is no principled way of setting it. Sometimes they set it to 0.5 or 0.1, but these are the things that you have to sort of estimate by trial and error. So you try different etas and see where you reach, and whichever gives you the minimal value, that is, you say, okay, this is the smallest value, right? Typically you try to err towards small, like you keep it smaller, because there you do not run the risk of overshooting it, even though you might take longer, right? Yes.
You said that you start from possible points.
Yeah. Right.
How can you tell if it covers all the minimums, or how many points you need to try?
Yeah, so that's a good question. So the question is, is there any guarantee that even if you do multiple runs, you would reach the minimum? And the answer is no. You do not know that, because in reality, see, in 2 dimensions or 3 dimensions, you can still visualize the function, right? But once you go beyond that, then you do not know how many minima or maxima there are, right? So there is no good answer for that. But essentially, what you do is you do it some number of times, right? And hopefully, if you are doing it enough number of times, you will reach the minima. But there is no guarantee. Yes.
In the derivative equation,
Uh huh.
I can figure out what is I need. That is the value of all the shapes.
Here.
Yes.
This is the value of x. So xi is the ith example, and xij is the jth value of the ith example. Remember, each example is also a d-dimensional vector, right? So j indexes that, because what is w transpose xi, right? You are taking an inner product between 2 entries here. This is W and this is xi. So this is xi1, this is xi2, and so on. And this is W1, W2, and so on till WD. So the J kind of goes through over this, right? So that's so that is this. Yes.
Is it possible to make theta change with gradient? I mean, the smaller the delta of gradient is, the smaller the theta becomes.
Right.
So,
Yeah, good point. So what I have presented to you is a basic vanilla gradient descent, but then there are many extensions of these. Some of them say start with some eta, but progressively make it smaller, right? And that also works. But there are no guarantees, but there are many smart ways to deal with this eta problem. One is, of course, you start with a big eta and then you slowly make it smaller and smaller, because as you reach the bottom, you want to be more accurate. When you're far away, you do not, right? But then that also depends on if your initialization was far away, right? But so that's one way. Another extension of gradient descent is the Newton-Raphson method, in which you do not have an eta. You compute the second derivative, which is the Hessian, and then you use that to figure out how much to move by. But that's a different algorithm. But that's a second. Those are called second order optimization methods, which are also looking at the second order derivative. All right. So yes, there are other ways to do that. Okay. Very nice. I'm spending a lot of time on this is because even for neural networks, we will be using gradient descent. So once we understand this, it will be easy to understand that part as well. All right. Yes. Right.
So we are starting with 0, 0, 0 as opposed to 2 values. How do you start the conversation?
You just set it. Well, yeah, that's a good point. Right. So let's say we are dealing with this one, right? So what you can say is that I'm going to start with W equal to 0. That's one possibility, and see where do I reach. Maybe with that initialization, I get stuck here. Then you randomly choose some other W. It's all random. So you know what your W range is. Then say, okay, next W, I'm going to choose this one. And then run my algorithm. There, maybe you reach here, right? Then you choose another W, let's say here. In that case, you reach here, and so on. So you do it many times. And then you say, use the one that gave you the minimum value, right? All right. So there are some issues with gradient descent. You are already pointing to some of them. But one of the biggest issues is that it's slow to converge. Okay, so convergence is a very big problem in optimization, right? In these simple settings, you might feel that it's not a big issue, but when you're dealing with large amounts of data, when you're dealing with very complex problems, sometimes algorithm doesn't converge at all, right? So you want it to converge as fast as possible, and the second thing is you do not want it to be stuck in local minima, right? But those are some of the inherent issues with gradient descent. So some of the other issues that we've just talked about kind of try to deal with that. But there is another algorithm which is very similar to gradient descent, which has been proposed to address some of these issues. Okay, so that is known as stochastic gradient descent, right? And we are not going to look at it in much detail, so I'm going to briefly explain it to you, and then you can go back and sort of think about it a little more. But it's a very attractive optimization algorithm. All right. So the way stochastic gradient descent works is that instead of computing the error with respect to the entire data set, now remember, when we were doing gradient descent, the error function that we had, where is that error function? Here. The error function that we had was computing the error over the entire data set, right? In stochastic gradient descent, what you do is you compute the error with respect to one data example at a time, right? So there's a double for loop there. So stochastic gradient descent, what it does is, the first step is the same, initialize W to something, anything. And the second is, right, and then you're still trying to do while not converge. The while not converge will be inside, I'm sorry. So for I equal to 1 to n, right? So you're looking at each training example one at a time, and then what you do is while not converge inside, and then you compute the wj, you update your wj minus eta yi minus w transpose xi xij negative of this, and then you keep doing that. So the difference between this and the gradient descent is that in the gradient descent you compute the error with respect to the entire training data set. So you can also call it a batch gradient descent, right? But here you're computing the error only with respect to one data point at a time. Okay, and then you are optimizing, then you're looking at the next data point and then optimizing. So it's little different than gradient descent, but so it's called stochastic gradient descent. The reason it's stochastic is because depending on what order the data comes in, your results might differ, right? So it depends, because this for I1 through n, this is you're cycling through your data, right? So if you shuffle your data, then your results might be different. So it's stochastic in that sense, right? So there are a lot of good qualities of stochastic gradient descent. I've listed a few here. Is that it sort of avoids, it has been shown, and there are a lot of theoretical analysis of this algorithm as well, where they have shown that it avoids local minima. It tries to reach the sometimes it has a better convergence. There are no guarantees, but a lot of times in practical settings they have observed that it converges better. And the important thing is that it has fewer computations, because at every step the amount of computation is less, because you're only computing the error with respect to one data point, all right, and then going on. So that way it's a little different. It works well in streaming settings. So for example, if your data is coming in an online fashion, first data point comes, then second comes, then third comes, right? So in that case, applying gradient descent might not be possible, because you would have to wait for all the data to come before you do the learning. Whereas in this case, you can do it in an online way. First data point comes, you do your gradient descent with respect to that data point, then the next one comes, and then so on, right? So that is sort of the difference between stochastic and gradient descent, right? And stochastic, from my perspective, I find that more useful than gradient descent because of these properties. But then there are other optimization methods as well, where you can just ignore gradient descent altogether, right? Any questions so far? Fantastic. All right, so I'm assuming that you all understand gradient descent and this thing very well. All right, so now let's quickly jump into our next topic, and then we'll do it next time. The next topic we are going to look at are neural networks. All right. So neural networks can be thought of as extensions of perceptrons. So today I'm going to sort of explain why, to motivate neural networks, and please think about it when you go back, all right? So one thing about perceptrons is that they give you a linear boundary, right? They always learn a linear boundary. So that is one property of perceptron, but oftentimes linear might not be enough, right? Oftentimes your data might be complex enough that you might want to learn a quadratic curve or a exponential curve or any other curve, right? any polynomial curve, right? But perceptrons don't let you do that, right? So the second thing is, what if instead of trying to predict one output, see right now we were trying to predict a y, right? And we said y could be a scalar. But what if we are trying to predict multiple outputs, for an example? You're trying to choose between multiple possibilities. So you no longer have to draw a line, right? So for example, in your handwritten digit recognition, the output that you want is it digit 0, 1, 2, 3, 4, or 9, right? So in this case, you have 9 possible outputs. You cannot use a perceptron to do that, because a perceptron is meant to only differentiate between 2 types of points, right? But here you want to differentiate between 9 possible points. So how do we extend 2 to 9, right? So that is one reason why we use neural networks. And the other reason is that we need to be able to learn non-linear functions, right? So that is what motivates neural networks. And one way to, so the story I was trying to build here is that perceptrons give you something, now you want more. To get more, what you can do is you can add multiple layers, and that gives you a neural network. So in a neural network, what happens is things blow up, right? So instead of having one input and one output, now you have introduced a hidden layer in the middle, all right? And then there are connections between all these nodes, and that gives you the output. And I'll explain how these connections work. But that's sort of the basic architecture of a neural network. You can put many hidden layers. Instead of one, you can put 20, right? And that is what nowadays people call deep neural networks. What we will see, and you will see in your assignment, is that when you add more and more hidden layers, things become more complex, right? So, well, what you will see in this assignment is that even having one hidden layer is complex enough. But in reality, having more hidden layers makes it even more complex. But then there are ways to resolve that as well. All right. So that is basically a brief overview, and we will pick up from there next time.